Okay, then we are heading over to the next talk, Convolutions in Overdrive, Maliciously Secure Convolutions for MPC, and Marc is giving the talk.
Welcome to the talk for our paper, Convolutions in Overdrive, Maliciously Secure Convolutions for MPC. So our work is concerned with MPC for PPML. So MPC is secure multi-party computation. Multiple parties want to compute a function together. Think of they want to evaluate a machine learning model together. One party has the inputs, the other party has the weights. And it can be also a more complex setting where there are client-server setting, clients have the data, servers do the actual computation, and also all the data can be distributed along a lot of parties. Then talking about security, the simpler adversary model is semi-honest, so adversary can observe data, for example, at some of the parties, or malicious security where parties can actively misbehave and try to influence the protocol, and we want to still have some security properties like the correctness of the result and to keep the inputs of the honest parties secret. Then MPC for privacy-preserving machine learning, or PPML. Assume we want to exactly do this, so secure evaluation of a machine learning model like before, and for a lot of machine learning models, convolutions are important. Not only the convolutional neural networks, but also other models can have like convolutions as part of them. And then in MPC, there are different approaches how you can compute the convolutions. So just basic generic MPC solutions would say a convolution is a lot of scalar multiplications and additions. Recently, there has been a lot of work to do efficient matrix multiplication, and there are ways to represent a convolution as a matrix multiplication. And some works recently, like directly did convolutions. So we identified that there is a gap if you look at the related work for privacy-preserving machine learning in MPC, that a lot of work is just semi-honestly secure, and we think that there are good cases where you might want the malicious security. And a lot of protocols are structured in a way that, for example, they wouldn't support this client-server setting. It's very specific. One party has to have the inputs, the other party has to have the weights. So this is what our work is doing. We present a maliciously secure MPC protocol with direct support for convolutions and any number of parties. We do this in a more or less classical two-phase approach, which is standard for the malicious secure protocols. We have an online phase where we do the actual computation on the data, and an offline phase where we pre-compute correlated randomness to make the online phase fast. And if you directly support convolutions, you're more efficient in both phases. Here, a more detailed overview of the related work. So as a base, protocols that directly do the multiplication, and there are different ways you can implement that. For example, with a lot of work just uses homomorphic encryption. So the first part is plaintext ciphertext multiplication. You can multiply plaintext with the ciphertext. Also ciphertext multiplication, which is a more expensive operation, and so-called rotations, which operate directly on the ciphertext, which also have some overhead. And we later try to avoid these. Then the next generation, more or less, of MPC protocols that do directly matrix multiplications. Here you can see, like, basically all the work uses these rotations. And then the few convolution works with that directly try to do the convolutions and cleverly operate on ciphertext to avoid the rotations. Then if you analyze the protocols, you see that basically just one of these papers goes beyond the scalar case if you look at actively secure protocols. And here everything that got light is also just very limited, like the two-party setup, where we wouldn't support this generic any number of servers client-server model. And this is where you would sort in our work. So we have two variants of our protocol, with both types of ciphertext multiplications, and we are actively secure and for any number of parties. And later we will compare in our evaluation the actively secure protocols. So convolutions, just on the same page here is an example. On the left is an image, in the middle a filter. To compute the convolution, you align the filter on top of the image, multiply all the pixels that overlap, sum them up and get 1 pixel of the results. Then you move over your filter, do the same thing again. You can move over your whole image. You can even move beyond your image if you define with padding what you should multiply there with. And then you can, for example, get something that is as big as your input image. And here in our example, we had to use 9 multiplications for each output pixel. And if you look at them, they're somehow redundant. All of them use the same pixels of the filter over and over again. So how do we approach this? As I said before, we want to pre-compute the convolutions in an offline phase with homomorphic encryption. So the standard scalar approach would start something like this. You sample a random vector, encode it in a way that it can be encrypted. Do the same for another vector. And then you can use the homomorphic encryption, for example, to add them up to get something that you can decrypt and decode to get the sum of your two input vectors. And then what you actually would do that for, not with addition, but with multiplication. In the middle, you have a ciphertext multiplication, and you get a vector that is like the element-wise product. And as I said before, this would be the plaintext ciphertext multiplication, where just one of the operands in the middle is encrypted. And in our paper, we introduce a more general framework where we have packing methods, which are this pack and unpack at the end. They're more general, that they can produce potentially many encoded vector of data. And then you can define this for any operation you want to compute. Also then find the matching operation in the middle on ciphertext to combine them in a way that you can do then convolutions, 2D convolutions, and also matrix multiplication. And yeah, again, the scalar case is also just a special case of this. And again, it also works if both of these operands are encrypted. So how do you actually find then efficient packing methods for convolutions? For this, you can look at polynomial multiplications, more specifically for cyclotomic polynomials, which happens to be exactly the underlying plaintext space of the homomorphic encryption you usually use for MPC. So every time you multiply ciphertexts, you actually get one of these polynomial multiplications. And here, a visual example, if we assume these are two polynomials where the colored boxes are the non-zero coefficients, then to multiply them, we shift one of the operands cyclically and multiply the coefficients that are on top of each other and sum them up. And we do this to get all the coefficients of our result, and that's a so-called negacyclic convolution. And obviously, this is very similar to just a 1D convolution. You have this cyclic shift, and a negacyclic means every time you wrap around, you also have to multiply by -1. So we can use this as a base to just get the 1D convolution quite easily. But you can do it also for more complex operations in machine learning, so-called 2D convolutions, where you have potentially a lot of batches of images. Then for every batch, you have like different channels. Think of red, green, blue of images. Then you also need a bunch of filters to get to your output, and your output should in a way that you have the same number of batches and potentially a different number of channels. And then each of the outputs is, you do a convolution where the channel of the image and the channel of the filter match, and you do this for all the input channels and then sum them up. and you do this then also for all the output channels you want to get, and all the batches. So the packing scheme for this would look something like this. So first you have your first batch of your image, then you leave some 0 coefficients, and then your second batch of the image, and your filter you pack in a way that it's just all the coefficients until where the second batch was started. Then if you do your ciphertext multiplication, you would get at first something where the wrong channels match. So for the first part, you see it's the red channel of the image and the blue channel of the filter. Then you move over, it's still the wrong things. But at some point, exactly the right channels of the image and the filter overlap, and you get first output image. Then you continue doing this, and you get at these regular intervals your parts of the output, and your unpacking is just you extract these slots where you have your output of the 2D convolutions. So how does this perform in practice? We implemented it and benchmarked it. Here's the example for if you run the scalar part, the first thing, the matrix-based implementation in hours. In a LAN network, ours is 28 times faster than the scalar part, 5 times faster than the matrix part. And if you go to a slower network that you could have in a client-server setup, we're 40 times faster than the scalar part, 3 times faster than the matrix part. So conclude, we presented first maliciously secure MPC protocol with direct support for convolutions. The offline phase is more efficient, also the online phase. You can find more details in the paper, as well as the formal framework, the actual MPC protocols, more evaluation, and our implementation is online. So these are the people and institutions that made this work possible, and yeah, thank you.
Okay, thank you very much. One question has been posted to Sulip, posted by Alessandro, and I'm reading it out. Is there a reason why you opted for sharing over a field instead of a ring? MP Speeds supports both for dishonest majority with malicious security.
Yeah, so like in the online phase, our whole online things would also work for the ring case. For the offline phase, I think the homomorphic encryption implementation just works for a field, and yeah, I guess that's the main reason. You can also do a variation of this probably for rings. I'm not exactly sure where you lose things.
Okay, good. So next speaker, please already put up your laptop. In the meantime, I have one question. So your protocol is secure against malicious adversaries, but maybe I missed it. But how do you achieve this? Can you explain it in the rough idea of what kind of technique you're applying to achieve this?
Yeah. So the more details are in the paper, of course. As the name suggests, we built on the Overdrive protocol, which does like this plaintext ciphertext or ciphertext multiplication securely for just a scalar case, and then with our packing method, we basically get convolutions for free.
Okay. And so hypothetically, if you would assume, okay, now you have your protocol, but for whatever reason, you think that semi-but honest attacker model is sufficient, could you somehow downgrade your protocol to gain efficiency?
Yeah, so part of what we built on was some existing packing methods and new packing methods that partially come from these semi-honest protocols. So yeah, you can just leave out some parts and then have a semi-honest protocol as well.
And then do you think it would be faster then, probably?
Yeah, it would be faster than this.
Okay, cool. Okay, then I would say thanks a lot.